To determine the rate law for a reaction, you have to purposefully set up an experiment to deliberately isolate the influence of each reactant. This involves doing trials where only the concentration of one reactant is changed. Once the data is collected, the following steps are done to write the complete rate law. Determine the rate exponents for one of the reactants. To do this, compare two trials where this reactant's concentration changes, but all the others stay the same. Looking at what happens to the rate, describe what occurs, and record your exponent. Repeat this for any other reactant in the reaction. Choose a trial and sub in the concentrations and rate into your rate law. Solve for the rate constant K, including the units. Then you'll have all your variables needed in order to write a completed rate law. Here's an example. I would first start by writing a general rate law. So rate equals K, the rate constant, times the concentration of the reactants raised to some exponent. Now, following step 1, I need to find out what the rate exponent m equals. I look at trial 1 and trial number 2. If I have a look, my concentration doubles. And if I compare my rates, they also double. That might be difficult to see because they're in scientific numbers. Remember, you can always use your calculator. If you take the rate for trial 2 and divide it by trial 1, then that will equal 2, or pretty close to it. If I'm comparing the concentration and the rate increase, they're proportional. If my concentration is times by 2, then my rate is times by 2. That means I have a first order reactant and my rate exponent is 1. I can now include that in my rate law. To finish off the rate law, I have to find the value of K. So I'm going to pick trial number 1 and sub in the concentration and the rate. And then I'm going to solve for K. Now the units for the rate constant depend on what unit of concentration your reactants are in and what unit you measure your rate in. So you have to find them independently. You can sub them in to this calculation here and follow along, but I find the units a little bit difficult. So I like to do them separately. My rate is measured in moles per second. That equals K times the concentration of the reactants, which is in moles per liter. That's indicated by having my H2CO3 in square brackets. That's raised to the exponent 1. Now, following our order of operations, you have to clear your exponents first. Because it's a rate exponent of 1, it doesn't really change anything. Now, I've got moles per second equals K times moles per liter. I'm going to divide both sides by moles per liter, but I'm going to divide a fraction by a fraction. So in order to make it easier, I'm going to multiply both sides by the reciprocal. Now having a look, I have moles divided by moles, so that cancels out. So therefore, K equals liters over seconds. Therefore, my rate law is this. Rate equals 0.0144 liters per second times H2CO3 to the 1. With this math equation, I could sub in any concentration of the reactant and predict how fast the reaction will go without even touching a beaker. Or if I wanted the reaction to go at a particular speed, I could use this and rearrange it and calculate the concentration I would need. Pause the video here and try out example 2. It's a bit tougher because there are two reactants. Remember, in order to determine the rate exponents, you have to do the reactants independently. Find two trials where NaCl changes but AgNO3 stays the same. Determine the rate exponent, and then follow the same steps to determine the rate exponent for AgNO3. Here's the answer for example 2. Start off by writing a general rate law. Rate equals K times the concentration of NaCl to the M times AgNO3 to the N. Now to find what M equals, I need two trials where the concentration of NaCl changes but AgNO3 stays the same. Looking at my observations, that will be comparing trial number 1 and 2. Now they always will not be in this order. Because my concentration doubled and my rate doubles, then I have a proportional increase, and M equals 1. To find N, I need to compare trial number 2 and trial number 3. This gives me two trials to compare where silver nitrate changes and NaCl stays the same. Now, the concentration of the AgNO3 increases by 2. And if you compare the rates, that increases by 3.86. Well, that's roughly 4. So AgNO3 is a second order reactant. I times by 2 and I increased my rate by 2 squared, equaling 4. So N equals 2. Now I need to find the value of K. I'm going to choose trial number 1 and sub in the rate and the concentrations. If I rearrange, K equals 0.0333. Now for the units. My rate was measured in moles per liter per second, and that equals K, and my NaCl was in moles per liter raised to the 1, and my silver nitrate was in moles per liter raised to the 2. I have to deal with my exponents first. Squaring this term would give me moles squared over liter squared. times moles per liter gives me moles cubed over liters cubed. Again, I'm going to divide both sides by a fraction, so I'm going to flip and multiply by the reciprocal. I have moles divided by moles, so that changes that to a 2. And I have a liter down in the denominator, so that can change that to a 2. So my units are going to be liters squared over moles squared times seconds. So my completed rate law will be rate equals 0.0333 liters squared divided by moles squared times seconds times the concentration of NaCl to the 1 and AgNO3 to the 1. Pause the video here and try out part B. How fast will the reaction go if you use 1 mole per liter concentration of each reactant? Here's the answer. If I sub in 1 mole per liter for each of my reactants, my rate will equal 0.0333 moles per liter per second of NaCl.